Welcome back to the module on dynamic approaches for AutoML. In this unit, we are going to talk about white box optimization approaches. Now, in the last unit, we have already covered the motivation behind why we want to move away from a black box view, but let me reiterate here. In the black box view, we only choose the input and observe the final outcome. There's no control over the box. We have no idea what's happening inside the box, and we're just taking the final outcome of this box and try to optimize hyperparameters, for example, with respect to that. In the gray box setting, for example, in the multi-fidelity optimization approach, we choose a single input but observe multiple intermediate outcomes. While we don't have full control over the box yet, we get some control and could, for example, decide to terminate optimization early by observing that we are stagnating in terms of performance after maybe the first intermediate outcome, or we're actually starting to get worse performance again, or something along those lines. However, in the white box view, which is the approach that we ultimately want for AutoML, we observe and control all details of an algorithm run. Right? So the goal here is really to replace hyperparameter heuristics or even complete algorithm components with a learned policy. And for that, let me quickly talk about iterative optimization heuristics. So iterative optimization heuristics, or IOHs, propose a set of solution candidates in each iteration based on a previous evaluation. We have already talked about learning being iterative in nature, right? So that is not just machine learning, but also the case for a lot of AI algorithms. And here in the statement, a solution candidate refers to a partially trained model. For example, just the weights of a neural network after 5 epochs rather than the full optimization budget having been spent. And the goal is to improve the quality of the successive solution candidates, right? So we want to take the previous solution candidates and build upon them and get to ever better solutions, not just stagnate or, like I said earlier, potentially even get worse. So the main component in an IOH is the proposal mechanism, or also the heuristic for how these new solution candidates are created. And we can really now take action here and adapt or configure these IOHs to make this proposal mechanism more efficient and much more successful over time. So one way of doing that is just by pure adaptation, right? In the first unit, we have already seen a potential for adaptation being just standard heuristics where community knowledge is codified in some simple rules which come with their own hyperparameters. And in the evolutionary algorithms, we often see that also in the form of self-adaptation, where the internal mechanism of the algorithm observes some statistics, and based on these statistics, the algorithm then decides how to adapt individual hyperparameters or other components such that the search progresses. So a very famous example of that is the step size adaptation, as is often used, for example, with something like a CMAES algorithm, which is linked in this reference here. But again, we have talked a lot about learning rates and deep learning already. And we know that we should, for example, start to reduce the learning rate when the loss stops improving, right? And exactly in PyTorch, you could find this with the reduced learning rate on plateau learning rate scheduler. Again, there are other hyperparameters attached to that, but generally speaking, it's all about figuring out when you're plateauing and how you then should adapt your learning rate. But there's also something in the realm of reinforcement learning, for example, the update constraints in PPO for the policy update. But that is just one way. Again, this can often be adapted and even further improved by adapting the hyperparameters or configuring the hyperparameters. But we could also directly learn a policy, and that's where we want to end up. That's what we really want to discuss in detail in this lecture unit, or in the overall module, right? So, and the goal of DAG is to learn a policy from data that adapts the hyperparameters of an IOH on the fly, right? So we have examples for that, and all of these are very interesting examples on how DAG has successfully been applied in the real world. So in the first setting, we have seen that you can learn learning rate adaptation for SGD and find better schedules than with configuring individual hyperparameters of some schedulers. There are also examples of learned mutation operator selection for differential evolution. So instead of always mutating the next offspring in the same manner with the same operator, you can also mix and match and get more diverse solution candidates over time and potentially find much better solution candidates in the long run than with just fixed operator selection or based on some self-adaptation mechanisms. And you can also adapt how often you want to interact with the system. So you can learn the interaction frequency of an RL agent, for example, in a dynamic algorithm configuration style manner. To summarize, the goal of white box optimization is to replace hyperparameter heuristics or even complete algorithm components with learned policies. And those learned policies can be applied to IOHs, which propose a set of solution candidates in each iteration based on previous evaluation. But IOHs can not only be configured with such learned policies, but they can also be adapted, for example, in a style of self-adaptation, as is often seen in evolutionary algorithms.